today is interrogate and alchemy. Mostly about interrogate. In the early days, before we even had Panda, we were doing development on SGI computers with our own little performer-based graphics engine that we didn't call Panda. We called it just the player. It was just the player. And we used Scheme as our programming language of choice. And so we had our player that was written in C++ and our scripting language was Scheme, and we needed a program that would interface between the two, and we called that program, we named it, our Scheme language we actually called SAL, Story Animation Language. And so the program that interfaced C++ to SAL was called Salivate. And we were really proud of that. And we used it for a while, and eventually it did a lot of the same sorts of things that Interrogate does today, but it was a simpler program. But it laid the groundwork for the sorts of things that we realized we needed. We eventually started to write Panda when we were moving off the SGI, and we also were getting away from Scheme at the same time. When we first started working on Panda, we didn't know what language we were going to use, so we wanted to write a program that would be language independent. Idea was we could write our C++ code and have this layer that would generate a wrapper function for any scripting language we wanted to write. That was the original design of Interrogate. At first, we started writing Panda with Squeak, a version of Smalltalk, and we used Interrogate to generate the interface layers for that. Eventually, we moved to Python, and we modified Interrogate to generate layers for Python, and the rest is history. Nowadays, of course, we're pretty much only using Python, and it doesn't look like we'll be using any other language ever again. So we just love Python so much. But we still got Interrogate, and even though it's got the lower level stuff internal to it that theoretically can support other languages, it's become more and more Python-like over the years. Let's see. Originally, of course, when we first wrote Interrogate, there was no other tool like it. We needed to write our own program to do this sort of thing because we were writing for Squeak at first, right? And there's nothing that did Squeak. Squeak was, by its nature, a program that interfaced only with Squeak. So we had to write our own utility to interface C++ to Squeak, and that was kind of hard. Then eventually, even when we went to Python, by that time there already existed Swig and another program called Boost. Neither of those was quite adequate at the time. Neither of them supported C++, for instance. And they had lots of other limitations that we didn't like. And we already had better than that in Interrogate. So it was much more sense for us to go from Interrogate and stick with using Interrogate. Since then, of course, Swig has improved by enormous leaps, and Swig is so much better now than Interrogate is in many ways. There's been some suggestion, and every once in a while it does come up, why don't we switch to Swig, because Swig is so great. The biggest reason that we haven't switched to Swig is that we've still got code that depends on Interrogate. The model that Interrogate uses is somewhat different than Swig's. And the way that we rename the functions is a bit unfortunate. For various reasons having to do with our history, we rename functions like, in find node or something like that. You might have a C function called find node, and as we all know by now, this becomes find node in Python. Oops. The reason this happens is because in Squeak, there is no punctuation allowed between the method names, so it had to be camel case like this. And so we got used to writing camel case functions. Well, actually, the reason it goes back even further than that. When we were originally using Salivate in Scheme, we would write a function. In Scheme, the convention between the letters is a hyphen. So you'd write a function called find hyphen node. Of course, that doesn't work in C. So what we decided to do was we'd write our functions in C with an underscore, and then we'd have our interface layer convert the underscore into hyphens if we were doing a Squeak type language. And then when we went to Squeak, we had to get rid of the underscore altogether, and we just capitalized the next letter to make a camel case. And then when we moved to Python, we had all these functions that already use the same camel case convention. We just stuck with it. So for whatever reasons, lost in the history of time, we rename all of our functions from this type of convention to this type of convention. And that means we're kind of stuck with the program that's going to do that. If we switch to Swig, we'd have to trick Swig into doing this sort of thing, which is possible. But it'd be a lot of work. Another thing that we do a little bit better than Swig is that recently, a couple years ago, Roger was spearheading this rewriting of the lower level interrogate stuff to actually do away with one of the interface levels on the inside. Interrogate actually, I think, generates code a little bit tighter than Swig generates now.
A lot tighter.
Yeah.
Once things have changed.
Yeah, and I looked at Swig recently.
Swig was slow.
Yeah.
It didn't do classes well.
Right.
At all. It was a fake.
It was kind of funny. The way that Swig does classes now is the way that Interrogate used to do classes. We kind of came to convergent evolution there, but then we took one step further in Interrogate.
We made native Pythons.
Right. And we're able to do that now because Interrogate is more focused on Python, and Swig is, ironically, Swig, which started out in Python, is now branching out to other languages, and is a little more limited to the things it can do in Python. Anyway. So for various reasons, in fact, there was, even a couple years ago, there was a guy on the Panda forum who started looking into what it would take to migrate over to Swig, and he actually made some good progress. He had this crazy thing where he'd do some sort of pre-processing of all the header files, generate a file that would feed into Swig automatically. Because one of the nice things Interrogate does is it just reads your header files automatically. There's no layout that you have to give for Swig. He would generate that stuff by automatic process and do all the case conversion. It seemed to be working. And then he disappeared, and then we never heard from him again.
Well, we challenged him on the speed.
Yeah.
We asked him, okay, now let's do a benchmark.
Yeah, so that was that. But anyway, it is theoretically possible to go to Swig, but I think for various reasons we'll stick with Interrogate, even though, you know, it's less standard, it's our own thing we have to maintain, but it kind of works. It's not broke, and it doesn't require that much maintenance, so it's not so bad. Okay. Let's talk about the high level of what we're doing here. When you're programming in Python, you're making function calls that look an awful lot like C calls. For instance, you might call find node, you know, fooby, I don't know, comma 2, I don't know what, I'm making up this function name, but you pass in a string, you pass in an integer, it looks like the same thing that you'd call in C. Syntax of Python is very similar to the syntax of C by design. But what's happening internally is completely different. When you call this thing in Python, what it's doing is it takes this list of objects, and each atom in Python is a Py object of some kind. So a string is a Py object string. Object. Even an integer is a Py object. So all of these things are actually structures internally. And this is a pointer, this is a pointer. And then the whole argument list is actually a tuple that it constructs on the fly. So when you call a Python function, it has to construct a tuple, it allocates a bunch of memory, builds up the tuple, and then calls the internal Python function and passes it that tuple, who unpacks it and does all the stuff it needs to do and returns a Py object in return. Of course, that's completely different from what happens in C when you're calling a function. And in C, when you get an integer, that's just an integer. It's a machine register, it's whatever the native calls an integer. A string is typically a pointer to an allocated memory of, you know, just pre-packed data. When you call a function, it just pushes these registers onto the stack and calls a function with a low-level machine call. All very fast, very machine native, completely different from what's happening in Python. So we need to have, in order to make this function call in Python that actually turns around and calls this C function internally, we need to have somebody on the inside that's taking this Python structure, this complicated Python structure, and turning it into the appropriate C calls. And that's what Interrogate is generating. So if you think in terms of a wrapper layer, in fact, let me take a step further. In order to create a whole class of methods and things like this that looks like the same C class. So let's take the example of NodePath. We have a NodePath class in C. And inside of NodePath, it's got some internal structures. It's got a pointer. You know, it's got some private data that you don't think too much about. But whatever it is, it's got a block in memory, and that's what gets stored inside of a NodePath. There's also a Python class called NodePath that gets created as part of the interrogate process. And like all of Python objects, it is a type of Py object, which means it's got some whatever Python mumble-jump it's got up there for the Python overhead, and plus it's got some more stuff that are just specific to our NodePath implementation. Specifically what it is, it's just got a pointer to the actual C++ node path. Might have a few more things we need to manage that pointer, like whether it needs to free the pointer when it's done and things like that. So when you're creating a Python node path, you're actually creating a Py object internally that's called node path, and it's got a pointer back to your actual node path, which exists down in the C level. But they're really two different objects in some sense. But we go through some pains to make them look like they're the same object. So if you were to call a method called setPos on your Python node path, this is actually a Python method, which is going to turn around. It's going to unpack the Python arguments you give it, maybe a sequence of numbers, and it's going to call the corresponding setPos method on this guy with the 3 numbers that you gave it. In fact, it has to do a little bit more than that, because C++ supports this whole thing of function overloading based on different types of parameters. Python doesn't actually support that natively. So this function has to, the wrapper function has to look and see what kinds of arguments you gave it. Figure out, is it a vec3? Is it a list of 3 floats? Is it a node path, comma, a vec3? Because all these are different flavors of setPos. And it's going to have to call the appropriate different C++ method according to which set of arguments you gave it. So you think about your Python class. Just by having a node path here and a Python wrapper here, it's got this list of hundreds of methods. And each of these methods is actually just a thin little wrapper class that's going to decode the arguments in Python, turn around and call the appropriate C function. And if the C function has a return value, it's going to take that return value and construct an appropriate Python object in order to return out of this method. OK? Clear enough? So the goal of interrogate is to set up this system. At the end of the day, after interrogate has done its job, every possible C++ object that you might want to talk about has a corresponding Python wrapper class. And every time you call any function in C++ that's going to return some C++ pointer, it's actually going to construct a Python wrapper and return that instead. And then when you call any methods on the Python wrapper, it calls the appropriate wrapper functions in here, which have been constructed to decode all the arguments, call the appropriate C++ function, decode the result value, and return that back. Right? Simple task. Let's see. Yeah, in the early days of interrogate, before Roger's optimization work, there are actually 2 different wrapper functions. And this is the way that Swig works, and it's because it's the most obvious way to do it. Interrogate itself would actually generate a wrapper function, and it would just be some hash code, FZ9X2, 1, whatever, some crazy name. And it would generate this interrogate hash code function, which would do the job of unpacking the arguments, calling the appropriate setPos method, and decoding the return value and returning that. But this would just be a flat function. And when interrogate was done, there would be a whole list of these thousands of flat functions for all the different classes. So it would just be global functions like this. It would also generate a database of the class hierarchy, and the class hierarchy and all the methods in each class, and it would reference the C++ method and say, this method is actually this crazy function name. Then we had another step called Jetpack code, which you would run, and that would read that database and generate a bunch of Python code. And in the Python code, it would actually generate a class node path. In the class node path, you could actually see the function that generated a setPos function, which would turn around and call this crazy hash function. So we had the 2 layers. Because of the way, it's made it much easier, because it's much easier to write this high-level stuff in Python, because it does a lot of clever factoring of the classes and the relation of the class objects and the inheritance hierarchy. That's why we wrote it in Python. I think Swig did it that way because Swig came out as C first and eventually bolted on C++ on top of it. But it means that whenever you call nodepath.setPos, it's going to call this Python level setPos, which in turn is going to call this C level setPos, which is still going to decode the Python functions again and call the actual C setPos, and it gets popped up back twice. So that's the double overhead that we had to pay every time. But nowadays, this is all built into C++ and interrogate. So instead of having a separate Python step that generates this Python level, this is all built into the code that interrogate generates directly. So there's only the one method. There's actually a C-generated method called setPos. that is actually a method rather than a flat function. And it does all the work of decomposing the elements and everything like that. And it's all assembled into a Python-like class down in C level. Now, it's not actually a true Python class, because a true Python class has to be defined in Python. But Python defines this thing called an object. And you can define an object and set all the methods on it. And it looks very much like a class. And so that's what we're doing down in the C level with the interrogate code now.
We're treating them as built-in types, basically.
Yeah, it's basically a built-in type. We still have the gen PyCode step, just because it was part of our process for a long time. And gen PyCode still does some useful things. In particular, it imports all the things that are in Panda modules. Actually, it generates in Panda modules.py according to what DLLs are in your search path. And that's, it's kind of handy. Some people complain about it.
We were supposed to get rid of it.
Yeah, I know. It was on our list of things to get rid of. It's one of those things. If it ain't broke, don't fix it. It still works. But nowadays gen PyCode is so fast because it doesn't really do that much work. So we never really minds it so much.
Yeah, it used to
anymore.
take like a minute or two.
Yeah, it used to take several minutes because it was actually generating lots of Python code.
Well, Python nodes still have, Python native objects still have a dictionary on them. Normally you can't access them. They're not visible to Python programmers. We put a hack in place. So you can write native object functions for Python and wedge them in up to into the dictionary. That's what we do with that code.
Yeah.
Because our intent was, there was like 5 functions that were just pain in the ass. We had to go write. We wanted to get rid of. Somebody was supposed to go write those in C. We never have. So nice project for somebody.
Yeah.
We can get rid of all of Gen PY code, and if we can get rid of those 5, probably 50 by now. But
yeah. But that's the other thing. But one of the things that GenPyCode does is it reads a bunch of Python native code in a directory called extensions native. And direct source extensions native, anytime you want to add functionality to one of these generated layers that doesn't exist in C. For instance, the nodepath collection has a method called asList, which returns an actual Python list corresponding to the nodepath collection. It's a handy function because the C accesses are kind of clumsy. And that function happens to be written in Python, and it's grafted into the shadow class by GenPyCode. GenPyCode finds the file called nodepath collection extension in extensions native, sees the Python code in there, and grafts it into this class it's generating. Now, so the fact that we can do that, some people get really excited about that and start wanting to add all sorts of extension functions to all of our classes. Of course, that's just going to be a maintenance nightmare if we go this whole way down.
yeah, we're probably better off we use inheritance for something like that instead of wedging it into the base class.
Well,
Carry a lot of weight.
ideally, I think I'd like to maybe improve interrogate to the point where it could return a Python list directly, so that we don't have to write things like asList to return a Python list.
Have to do what again?
So the reason we have asList is because interrogate can't return a Python list. It'd be nice if we could figure out some way to make that happen natively, so that we don't have to have extension functions in that.
Yeah, I think we're saying the same thing.
Yeah.
Translate arrays into lists or tuples.
Right, something like that. The problem is the interface is not quite the same. You wouldn't return an array from the return value.
Yeah.
But Python doesn't have pass by reference, so how would you do that? It's not quite clear.
You'd have to construct one.
Yeah, we have to have some convention.
Yeah.
We have to have some convention for maybe a method that indicates the iterating through the elements and the length of the array. And then we could, by some naming convention, magic naming convention, build a list.
Yeah. Okay.
But we'd have to work that out. And there are a few other things we'd have to work out. But in the meantime, we've got this extensions native, and people see that this is here and like to add extensions. And every time we add a new extension, that makes this job that much more difficult, because we have to go and figure out how to make that extension work in the new system too. So, although we've got the extensions native system, you can use it if you need it, but please be cautious that you don't use it inappropriately. Okay. All right, so interrogate itself. Interrogate is a pure C++ parser in some sense. That is to say, it reads standard C++ syntax and understands it so that it can know what the function prototypes are. Mainly it reads the header files. So for instance, in nodepath.h, we got the definition for nodepath. And it's got a bunch of methods. It's got, at some point, it's got the publish keyword. And a bunch more methods, and one of them might be, for instance, void set pause. Load X, Y, Z, you know. That's the right idea. Anyway, so interrogate actually reads the header file, sees the class node path, understands that it's defining a new class, sees a publish keyword, and this is actually a pound define in our part. We've cleverly pound defined it publish to be, if you're compiling the system with a regular compiler, we pound define this to be public. So publish is actually seen by the compiler as just a regular public keyword. And if you're compiling it with interrogate, it pound defines into a different keyword, which is a special keyword that only interrogate knows. I think it's under published. This is a special keyword that interrogate discovers and means everything in this scope is intended to be exported to the Python level. And then it sees this method and understands the return value, the name of the method, and the types of the parameters. And it can understand quite a bit of C++ syntax. It understands about array parameters, it understands about other class object parameters, and even understands templates to a certain extent, so it can understand STL structures and things like that. At the end of the day, interrogate is almost a compiler in the sense that it can understand C++, almost any C++, standard C++ header file or even body file you throw at it. It doesn't compile in the true sense because it doesn't generate object code. What it outputs is a database of class hierarchy and methods, and also a C++ file that when you compile the C++ file, it will generate the wrapper code that will do all this Python magic. Now, the fact that interrogate is a C++ parser. At the beginning, when we started writing this, we thought this would be a great idea, because we were tired from the old days of Salivate of having to re-encode all the function parameters in special syntax and tell the interpreter what kind of functions we wanted and what the parameters are, because you know that always gets out of sync. And this is a problem, a real problem with Swig-generated interfaces, is that it gets out of sync. And this is why, for instance, PyOgre is always out of sync, because somebody has to go by hand every time they add a new method, every time they add a new parameter. Somebody has to go and change the interface specification to match the new specification. So one of the great things about interrogate is you don't need to do that, it just reads the code and figures it out. And yeah, it is kind of nice. It's got some downsides to being a C++ parser. First, as it turns out, C++ is not an easy language to parse. You think it is, it's based on C, and C is an easy language to parse, right? Turns out C++ is not at all straightforward. As soon as they bolted on the template stuff, it just all went downhill. You can no longer do recursive descent parsing on the language. We tried, it actually does do recursive descent parsing in work. I mean, we wrote a Bison grammar to parse C++, but it was a major pain in the keister. If I knew then what I knew now, we probably wouldn't have gone that route. Although, nowadays I understand that there are extensions to GCC to do this sort of parsing for you and just hand you an XML file. I'd love to use that. But we wrote our own parser, and it still kind of works. One of the other downsides to writing a parser is that it turns out that in every system header file, in every compiler in the world, there's all sorts of native stuff that is not standard C. All the GNU header files on Linux, all the Windows header files on Windows, they all have all these crazy keywords that nobody ever heard of. They mean something to their particular compiler and not to anybody else. And interrogate just chokes on those. Now, interrogate can't just ignore them, because a lot of times those header files are defining important types that you need to know that actually are types, if nothing else. The very declaration, foo bar, how about this? This means one thing if foo is a type, it means something completely different if foo is an integer. So you have to understand if foo is a type or not in order to correctly parse the syntax at all, or it's going to choke. So we mainly work around this problem with the system header files by providing a shadow class, or shadow header file. And there's a directory called parser inc. And this is in dtool. if you go in detail source parser Inc., you'll see a bunch of header files. And these are, like types.h, windows.h, winsock.h, all these crazy system header files that define all sorts of crazy things. And if you open them up, most of them are very short. And they might do something like type def handle, I don't know, let's say int handle, for instance. And this is just type defing handle as a type. It doesn't even matter if we get the type right. Who cares? We're not actually trying to pass the handle back into Python. We just need to be able to parse some code that references the handle down here. And we can't parse a whole windows.h. So we just define handle as an int, and who cares if it's actually an int or not, as long as it's just a type. So we have lots of header files that define just like 5 or 6 types like this, and that's all we really need to parse our header files. We've cleverly put up, when we run interrogate, it runs a lot like the compiler does, but it has a different set of command line options. And one of the command line options it has puts parser Inc. first on the included search path. So that's how that magic works.
We also use this as the primary way to get external libraries safely into Panda too, because most external libraries have the same issues there, including Windows or types.h or something.
Yeah, a lot of times when you're first bringing in an a third-party library into Panda, you run into this trouble with the header files that come with that library. So you have to play this game and just type def out, project out the types that you need, and the rest of them you can just ignore. Sometimes these header files are just completely empty, and that's okay too. Let's see. All right. So as we're compiling the source code, well, let me talk about how the source code is structured. If you haven't looked at the Panda source code lately, or in the past 6 or 7 years, you might not have noticed that there are source directory and metalibs directory. So inside the source directory is a set of other directories like express and util, pgraph. And inside the metalibs directory are things like Panda Express and Panda, and Panda DX and all that stuff. So fundamentally, the metalibs corresponds to roughly the DLLs. So, for instance, we get a libpandaexpress.dll this way. .dll. And the individual source directories here are mainly just are logical groupings. They don't correspond tightly to the DLLs. But you collect several of these directories together into a bunch of, each directory compiles into a bunch of obj files. And then we link those objs into libpanda.dll down here. This is part of the whole build structure. And the reason we do this is lost in the midst of time too. But it has to do back with the origins in Unix. In Unix, by the way, this relationship is not true. libexpress, when you compile the express directory, directly produces libexpress.so. And util is libutil.so, pgraph is libpgraph.so. So basically, we've got a DLL for each directory. We also construct these metalibs directories, libpanda.dll.so, libpandaexpress.so, but they're just tiny little files that just have links to the SOs over here on the Unix case. But it turns out on Windows we had to make these big DLLs for various fiddly reasons having to do with the way that Windows exports symbols from the DLL. In Windows we don't compile individual DLLs for each directory. We only compile a big DLL for several of the smaller directories. This means that when we come into Python, we're basically importing libpandaexpress or libpanda or one of these DLLs down here. Python doesn't import any of these. Even on Unix, we just import the big ones. So as far as Python's concerned, these guys are the modules. And these guys simply define classes and methods and things that build up the modules. All this is relevant because the way that interrogate works, it knows about this structure. When we compile the source tree, as we're visiting each directory that makes up the constituents of the modules, first thing we do is compile the source code in the directory, C++ code, and produce a bunch of obj files. And then we run interrogate on all the files in that directory. And interrogate will read all those files, parse them, and understand them, and generate one big C++ file. And you can find this inside the opt3.-sigwin directory if you look. For instance, there's a libexpress underscore igate .cxx. Now this is a huge file, and it's all generated code. And this is the output of interrogate on Express. And this contains all the generated code that's necessary to construct all the objects and all the class objects defined in the Express directory and all of the methods, all the wrapper methods for the methods that we expose from the Express classes and so on. Similarly, there's one for the util directory, the pgraph directory, and all the other directories. So we compile the C++ files into OBJs. We run Express, or we run interrogate on the C++ files and generate this file. And then we compile that file into an OBJ. You can see this happen if you watch the Panda build. And then at the end of the day, after we've got all these OBJs, we're going to link them into a DLL. But before we can do that, we run a different program called interrogate module on the DLL directory. Interrogate module generates another file, which would be, I think it's called _module.cxx. It would be libpanda express _module.cxx. And this file just contains the boilerplate stuff to bootstrap the Python DLL. When you import a DLL into Python, it expects to find a certain function, and it's going to call that function to initialize that Python, the DLL. And that function is named init lib, whatever the name of the DLL is. So the interrogate module program generates this module file, which has that function for it. And that function, all it does is going to turn around and call the corresponding initialization functions for each of these individual components. And then the initialization functions for the individual components will set up all the appropriate tables that are necessary to build the class objects that will be ultimately returned into Python. And it all gets constructed and built into this great big namespace, which is then available to the Python executable. All right? So fundamentally, the two steps are interrogate, which generates these individual files, and interrogate module, which generates this one file, which references the individual files. Then at the end of the day, these files are all compiled together, linked into a DLL, and we can import that DLL in Panda, in Python. Does that make sense at some level? There's one more sneaky trick that Python did to us. Python 2.5 changed the rules a little bit. In Python 2.4 and below, you can just import a DLL. In Python 2.5, you can no longer import a DLL. You have to import a PYD file. And this, I understand why they did this, because there's a bit of a security issue with being able to import a file. In Python, you can just say import libpanda, and if it finds a libpanda.py or libpanda.so or PYD or libpanda.pyc or libpanda.pyo or libpanda.dll, it's going to look for all these files, and it's going to find the first one that matches, and it's going to import that one. And we discovered this because people use this as a breakpoint into our code. A hacker would put a libpanda.py in his Toontown directory, and as soon as he imported that, well, suddenly he's running his own code. So one of the things that Python 2.5 changed is that you can no longer import a DLL by name. You can only import it if it's called .pyd. And a PYD is just a DLL with the PYD extension. But this causes problems, because that means we cannot import libpanda.dll unless it's named libpanda.pyd. Well, okay, we could just name it libpanda.pyd, right? But except that libpirates.dll is going to want to link with libpanda.dll. It's not going to link with libpanda.pyd. So what do? We have two of them, a DLL and a PYD, but now if we load them both in, they're going to duplicate code. I've still got a real problem here. So Python 2.5 actually is not going to work for us. Unless the long-term solution would be to break out this code and compile just this code into a PYD, which links with the DLL. So we'd have all the C++ code in the DLL and all the generated code in the PYD. And yeah, we could do that. It's not that hard. We just have to restructure our build scripts a bit more. In fact, some of the guys on the Panda forums found a shorter-term workaround, which is you can overload the import module in Python and say, OK, I really do want to load a DLL. And that's what they've done. So we'll stick with that, too.
So we're not planning on upgrading to Python 2.5 anytime soon?
If we do upgrade to Python 2.5, we'll probably do the shortcut trick. And yeah, I'm ready to go anytime you are. Let's see. Okay, that's most of the guts of interrogate, without getting into the little fiddly bits of how it's actually written on the inside, which yeah, it's some scary mess, but it works. And mostly we haven't had to mess with it these days. Questions about the process, about any of these things I've been talking about so far?
I think alchemy would make more sense.
We may not have time for alchemy, sadly.
It's all based on the principle of equivalent exchange, I'm told. Okay, there's a few handy features to know about. We already talked about the extensions native, and you can put code in there. There's also a extensions directory, which is the older form of this. Before we had the new style native classes, we had the old style 2-layer step with the extra Jetpack code. So if for some reason we ever went back to that, which I can't imagine us ever doing, we would load the code out of extensions. Probably we're never going to go back, so we should probably just delete that code out of the extensions directory because it's just confusing. But we have direct source extensions and direct source extensions native, and they pretty much duplicate the code, but the extensions is for the old style system that we're not using anymore. Extensions native is the new style system.
Does anybody else use it?
Don't think so. It's been a couple years now. So anyway, if you wanted to add an extension to your C++ class or to your Python wrapper, you would put it in extensions native, not in extensions. But please consider carefully what you do. Another way to make Python-aware features is to write wrapper functions in C++ that actually know about the Python C API and directly handle the Python arguments instead of. So by default, interrogate will take all of your C++ or all of your Python arguments and turn them into C++ arguments and pass them to your C++ function. Sometimes you want to be able to handle a Python object that really doesn't translate well into C++, like a Python list or a tuple or something like that, and a dictionary. Maybe you really want to write a function that knows about Python native types and wants to do something specifically with this Python native type. Interrogate will allow you to do that. You can just write your C++ function to receive a PyObject parameter, or any number of PyObjects parameters, or whatever. You can even do a PyObject, int, or whatever. Interrogate sees this and knows PyObject means any old PyObject. Whatever the first parameter you pass to foo in the Python level is going to get passed here, whatever that is. And you can write your function to decode that as it should. Also, you can write your function to return PyObject. And interrogate sees this and knows that, okay, you promise that you're going to follow the Python C conventions and return an appropriate PyObject with its reference count incremented just like Python wants you to do. It won't question anything that you're going to return. So that's a handy trick if you want to actually do some Python native stuff. We take advantage of this in the DC parser class to integrate tightly with the network layer. So for instance, we're passing functions into the DC parser that we're passing Python function objects into the DC parser that eventually get called back. And that's the only way you can do that, of course, is by passing a PyObject. If you do this, you should probably put this code in here, if diff have Python. Especially if you do this in any part of the public part of Panda, because Panda does theoretically compile without Python. If you don't protect it like this, you'll break anybody who happens to be compiling Panda in the absence of Python.
Or even doing a minimal build for testing before they start doing their full build.
Sure. Let's see. There is a... one of the things that interrogate does in each of the wrapper functions it generates is it listens for the nsert macro. So in Panda, we use this a lot. We have nsert R and nsert V. And these replace the system level assert macro. All of us C programmers know about assert, right? It's such a great thing. You need to use assert all the time. Assert just means I assert that this is true, and if it's not true, then something is very horribly wrong and I want to crash and burn. And it's a useful thing to just double check your parameters, because if you don't put this assert, you might just crash mysteriously later. But if you put an assert to detect when something has gone horribly wrong early, then you know where to look when something goes wrong. It's a great thing. Problem with system level assert is if you fail a system level assert, it exits the whole process, which is kind of inconvenient when you're running along in your Python interpreter and you call this method which detects that something is horribly wrong, and suddenly your interpreter goes away. And all your code you've been working on is gone, and all the variables you've been saving are gone, and you're very sad. So for that reason, we have our own assert macros, which don't actually raise an exception or abort the process in any way. All they do is return from the function that they're in. That's why we have two flavors, assert R and assert V, because functions either have a return value or they don't. Assert R has its assert condition and a return value that it should return in case it fails. And assert V simply returns void. Now, if any of these is triggered, then the Python wrapper code, so after the Python wrapper has called your C-level function, it checks the flag to see whether one of these assert functions was triggered recently. And if it was, then it raises a Python exception. So that's what happens when you use the inassert macros in C. It turns into a Python exception, which interrupts your interpreter nicely, takes you back to the Python prompt, and you can fix whatever the problem is. There's a few other macros that are less often used, but are sometimes handy. Inassert underscore raise. This is a function that simply sets the exception flag so that when this function returns, it will trigger the Python exception that you name and pass the string, report the string as the exception string. It doesn't actually return from the function itself. It's up to you to return. But this is sometimes handy if you want to report a meaningful error to the Python process, other than n assertion failed, n unequal to 0, which isn't always meaningful. Sometimes you want to say, your model was not loaded properly or something like that. Some meaningful error message to the user you can pass an inassert raise. Good to know about. Let's see. A few other things. Sometimes you have a global function. For instance, we have a global function called compose matrix as an example. This is not part of any class, so there's no way to put a publish keyword to expose it to Python. But you can still expose it to Python. We have another pair of keywords. We call it begin publish, begin underscore publish, and end underscore publish. So this is used to bracket things in the global scope that you want to expose to Python. Also, this works on pound define symbols. You can put a bunch of pound defines inside your begin publish sequence, and they'll get exposed to Python also. Let's see, one more thing, sneaky trick about interrogate. There is a series of files you'll find in some of the C directories with .n extension. For instance, there is a luse.n in the linear algebra in our linmath directory, the .N. N stands for interrogate, and this is just a series of commands, fiddly little commands to interrogate. Every once in a while, you need to actually control what interrogate's doing in a little fine-tuned way. For instance, luse.n says, I want to export this particular template and this template and this template, not these things, don't worry about that bit. And it has a lot of fine-tuned control. We don't have to do that very often, but it's good to know that you can do this. In general, any star.n files in the compilation directory will be loaded and looked for interrogate commands. We try to limit it to just one per directory, otherwise it gets confusing. So, okay. All right. Happy interrogating.